We skip now over the first half of the 20th century to the radical change that occurred in the intellectual world after the Second World War. I've previously described this as the cognitive turn. There were a number of contributions here, a number of reasons why the ground shifted under the science of the person. Primarily, this was because an entirely new set of metaphors and a new formal language became available in which one could discuss such notions as information. The guiding metaphor of the computer came into being at this time, and it was also the time at which the pipe dream of artificial intelligence was cooked up. This cognitive turn needs to be understood in a very broad context. There were developments in psychology, in linguistics, in formal mathematics and logic, as well as in what we now call computer science and the development of cybernetics, all of which came together to provide a rich sort of range of resources for thinking about old problems. One of the central elements here is the theory of information developed by Claude Shannon and others at Bell Labs. It is worth noting that this rather technical theory takes a specific view of information that does not map easily onto the way we use the term information in everyday life. We will continue to use the word information loosely in this module and not worry too much about that, but it's worth remembering that that word has complications. Now, a central figure here, for our purposes, is Warren McCulloch and his friend Walter Pitts. They worked together for very many years. Pitts actually lived at Warren McCulloch's house. Walter Pitts plays a bit of the role of a sidekick here. It was always Warren McCulloch who was in the limelight. They're both true geniuses of a very, very spectacular sort. McCulloch was a psychiatrist, an epistemologist, a poet, a militarist, what you might call a theological engineer. Strange characterizations. He was a very forceful personality with a rich vision. When Warren McCulloch went to do a PhD, he walked into his future supervisor's office, and the supervisor said, "What is it you want to study?" And he said, more or less, I'll paraphrase, he said, "I want to know what is a number that man may know it, and what is man that he may know a number?" I'm not sure he ever resolved that question. Together, they published a series of very, very influential articles. And usually it's, as I said, Warren McCulloch who gets the mention, but Walter Pitts is really worth looking into. They both have very interesting life stories. Pitts ran away from home and lived somewhat on the outside. He was a mathematical genius. He was corresponding with Bertrand Russell, who offered him a place in Cambridge University when he was only 15. Pitts's father didn't like him being mathematical, and that was why he had to run away and live a shadowy existence. So the Wikipedia story of their lives is worth diving into. There's some very poignant moments there, and they ended up dying in separate wards in the same hospital at the same time without knowing that each of the other was there. From our point of view, this article from 1943, A Logical Calculus of the Ideas Immanent in Nervous Activity, is our seminal point. This is where the entire field of artificial neural networks was born, in this article. The title might strike you as odd. Immanence is something you will usually find in theological discussions and not certainly in engineering discussions. McCulloch's motivations were religious. Immanence for him is the immediate presence of reality, or God, or experience. We have lots of different words that don't really mean much. Transcendence refers to that which is beyond, immanence to that which is present. And he wanted to understand how the brain could give rise to the rich notion of what we might today call consciousness or ongoing experience. He was not interested in building simple mathematical models to solve puzzles, which is what we'll be doing. shockingly. Let's have a quick look at the abstract. Because of the all or none character of nervous activity, neural events and the relations among them can be treated by means of propositional logic. Let's stop right there. The all or none character of nervous activity refers to the discrete nature of the spike as found in the neuron doctrine. A spike is either present or not present. We never find half spikes. In this article, McCulloch and Pitts will go on to show that one can create a very simplified model of connected units, or neurons, which can implement what he calls propositional logic. This is basically Boolean logic, which was, at this stage, still considered to be the foundation of the whole of mathematics. Warren McCulloch here is, whether he knows it or not, subscribing to the old mystical and religious doctrine of Pythagoras, who saw the entire cosmos as number. So he's trying to take the formal language of logic, which, if he can capture it, will give him the whole of mathematics, and relate it in some way to the structures of the nervous system. The neural spike is central here because it's an all or nothing affair. And to McCulloch, that seemed to map, perhaps, onto what we now call the one or zero, true or false notion of the bit. That is an element in a computational system which is either on or off. This basic binary logic underlies all computing since, of course. And if you can implement basic logical functions, you can do an awful lot. The nature of computation is such that if you have the right set of primitive functions, you can then build systems of arbitrary computational complexity. So their goal here was to map from the messiness of the nervous system to this pristine formal world of logic. And if that could be done, then one could view neurons as if they were carrying out a form of logical computation. You probably have heard people discussing brains as if this was simply a given, as if we knew that brains compute. We know no such thing. This particular hypothesis, pursued with this strong religious agenda, warranted the development of a simple computational model in order to think more deeply about brains. The intellectual climate of the time was very receptive to this because of the novel vocabulary of information and computation. The work of Turing needs to be mentioned here as well. And so a whole new field was born. Here are just some of the illustrations from that 1943 paper. And there the little triangular elements are individual computing units, which are connected in series, all detail washed away here. If you could see these as computing a sum and then setting themselves to be either 1 or 0, you can understand networks of connected simple units here as if they were conducting logical computation. The table on the right here illustrates an example of the kind of function that logicians care greatly about. This is the table for what we call the AND function, which we will meet later on. The AND function considers two inputs, each of which can be either true or false, or 1 or 0, and an output, which is 1 or true, if and only if both inputs are also true or 1. You can see it's called a truth table there. That's an example of the kind of function that Warren McCulloch was thinking of. Now there have been many simplifications that just slip by us. First of all, of course, we're treating neurons as if they were the only relevant element in the brain, and we know that not to be true anymore. The notion of a spike has been reduced to the notion of a bit. So spikes were Warren McCulloch's motivation. The on-off nature of the spike inspired him to develop this kind of model. But all details about the spike have now been washed out. And within the kind of model that we will be developing here, individual spikes are no longer represented. Rather, a given unit will have associated with it a number which we'll call activation. And you can think of that roughly as the mean spike rate over a given time, although we have to be honest and say what we've done is abstracted away from what neurons are doing in order to move into the field of logic. The basis of the neuron doctrine, which we met in the previous lecture, provides the rationale for considering these units as simple elements that sum up their inputs, calculate an activation, and that generates this activation then becomes their contribution to other units. One more massive simplification that happens at this point is that time will now be discretized. As I said, the timing of individual spikes gets lost here completely, and we will consider time as if it consisted of a sequence of discrete intervals, so we can ask about the state of the network at time 0, then at time 1, then at time 2, and so on. So we've discretized time. For all these reasons, I choose not to refer to the units in a so-called neural network as neurons. We will call them units in this course, and they are, it's true, inspired by the brain, but no more. They are not to be taken as realistic models of what neurons do or what the brain does. Now, a lot has happened since then, but the computational view of the brain became extremely popular and powerful and still is to this day. And we have to briefly acknowledge at this stage that we have a tendency to fantasize about the brain and to project our pre-existing ideas about the person, about identity, about such mysteries as consciousness and experience, onto this lump of fatty tissue. It's notable that if you do some Google image searching and look for brains, what you'll find tend to be pictures like these. They're usually blue. They often have radiating elements coming out of them. There's a suggestion that this is the point of with the magic plugging in of the individual to the cosmos happened. These kinds of views have nothing to do with real brains. We recognize them, of course. They're familiar in art. Here's a medieval picture of the same kind of direct contact with God, illustrated here for, I'm not sure who the person sitting down is, possibly the Virgin Mary. Remember Warren McCulloch's original motivation here. The view of the brain taken here is pre-scientific. It also inherits a lot from German Romanticism. Here, for example, is one of these very classic pictures of the brain emanating out into the cosmos, and there on the right is Caspar David Friedrich's very, very famous picture that captures the solitary individual gazing out over the entire world. These kinds of currents motivate this kind of modeling. Strange. It's also at this time that the somewhat fantastic notion of artificial intelligence was born. Now, intelligence is a very, very problematic construct. There is no universally agreed notion of what intelligence is. Intelligence tends to be treated as that which some powerful individuals in a society accord to themselves and not to others. Don't believe that we can ever measure intelligence or that there's three kinds of intelligence. Those notions are nonsense. But at this time, the rationalist tendencies, this very abstract notion of intelligence as a purely intellectual character, of experiences largely intellectual and abstract, was current. And under those circumstances, it seemed reasonable that one could imagine building an artificial object that was either sentient, that is conscious, or intelligent. Nobody's ever defined these concepts to anybody's liking. McCulloch's vision was this. He wanted to understand the basis of experience from a religious point of view. His legacy, which we will be exploring in this module, develops the notion very differently. And the term artificial intelligence has changed its meaning in the subsequent decades so that its current use is completely unrelated to its origins in this particular intellectual climate. And with that, in the next video, we'll move on to the simple McCulloch Pitts model.